Tonight, we're going to explore something that is happening to you right now, in this very moment, as you sit or lie, in whatever quiet place you've chosen for this. Something invisible and ancient and almost unimaginably numerous is passing through you, through your skin, through your organs, through every cell in your body, through the chair beneath you, through the floor, through the bedrock of the earth itself, as though none of it were there at all. Every second, approximately 65 billion of them pass through every single square centimeter of your body. From a single source alone, just from our sun, 65 billion per square centimeter per second. And they don't stop when the sun sets. They flow through the planet, through the whole turning sphere of the earth, and come up through the ground beneath you and continue on into the night sky, as if the entire world were simply not present, as if matter, the stuff you're made of, the stuff everything is made of, were the thinnest possible gauze stretched across an infinite room. They are called neutrinos, and they are one of the most staggering, humbling, deeply mysterious particles in all of physics. Before we begin this journey through the strange and beautiful world of the neutrino, if you find peace and wonder in these slow explorations of the universe, please consider leaving a like or subscribing to Sleepy Universe. It genuinely helps this channel grow and reach more curious, restful minds. Now, let's settle in. Section 1. The ghost particles all around us picture the universe as seen not by our eyes, but by some extraordinary sense tuned to detect neutrinos. The picture would be almost incomprehensibly different from the one we know. Every star in the night sky would blaze with an entirely different kind of brilliance. The sun, familiar and warm, would no longer be just a sphere of glowing light, but would be revealed as an enormous storm of particle creation, flooding the solar system with 200 trillion neutrinos every single second. Our galaxy, which looks like a pale band of stars when we see it from a dark country hillside, would be revealed as a churning sea of these invisible streams, a cosmic ocean of particles born in stellar cores and supernova explosions flowing in all directions through the arms of the Milky Way. And the cosmic background, the very oldest light we can detect from the early universe, would have an invisible companion, a neutrino background born in the first second after the Big Bang itself, older than any atom, older than any star, flowing through everything forever. This is the real texture of the universe, the visible light, the radio waves, the gravity we feel pulling us toward the Earth. These are just one language the cosmos uses to communicate with us. Neutrinos are another far more ancient and prolific language, one that we have only very recently begun to learn to read. The word neutrino is Italian in origin. It means simply, the little neutral one, and that name captures two of the particle's defining properties. It carries no electric charge, and it is extraordinarily, impossibly small. Neutrinos are one of the fundamental building blocks of matter described by the standard model of particle physics. They are leptons, placed alongside the electron, the muon, and the tau, and their corresponding neutrinos in the family of particles that do not feel the strong nuclear force. Each charged lepton has its own neutrino partner. The electron has its electron neutrino. The muon has its muon neutrino. The tau has its tau neutrino. And each of these has an antimatter counterpart, the antineutrino. Neutrinos interact with matter only through the weak nuclear force and through gravity. The weak force, despite its name, is actually extraordinarily potent at the subatomic scale, responsible for radioactive decay and for the nuclear reactions that power stars. But the range of the weak force is fantastically short, confined to distances smaller than the nucleus of an atom. This means that for a neutrino to interact with any piece of matter, it needs to come astonishingly close to an individual proton or neutron, closer than the proton's own radius. The probability of this happening in any given encounter is almost incalculably small. To put this in perspective, consider a wall of lead. Not a thin sheet, not a meter of lead, but a wall of solid lead 1 light-year thick. That is approximately 9.5 trillion kilometers of pure dense metal. If you sent a beam of neutrinos at that wall, the average neutrino would pass through it without interacting, without slowing down, without deflecting, without leaving the faintest mark. The entire lead wall, a light-year deep, would be functionally invisible to it. This near-perfect ability to travel through matter without interaction is what makes neutrinos both extraordinary and extraordinarily difficult to study. And yet, understanding them has become one of the most pressing missions in modern physics. Because as we will discover together tonight, buried inside the physics of the neutrino are hints about some of the deepest mysteries the universe holds. Why does matter exist at all? What happened in the first moments after the Big Bang? How do stars explode? What is the nature of mass itself? All of this somehow connects back to this small, ghostly, profoundly abundant particle slipping through you right now. Section 2. The birth of an idea. Pauli's desperate hypothesis. To understand where the neutrino came from, we need to go back to the late 1920s and into a problem that was tearing in the heart of physics. The problem was called beta decay. When certain unstable atomic nuclei decay, they can emit an electron. This process, called beta decay, had been observed and studied for decades, and physicists assumed they understood it. An unstable nucleus would shed energy by kicking out an electron, and that electron would carry away exactly the energy difference between the initial and final state of the nucleus. Conservation of energy demanded this. Conservation of energy was, at the time, considered one of the most sacred, unbreakable laws in all of science. But the electrons didn't behave the way they should. They came out with all sorts of different energies. Not a fixed, predictable energy, but a continuous range of energies, from near zero all the way up to a maximum. The energy spectrum was smeared out, continuous, inexplicable. It was as if some energy was simply disappearing. The great Niels Bohr, never one to shy away from radical ideas, actually suggested that maybe energy conservation simply didn't apply in these nuclear processes. Maybe the sacred law wasn't so sacred after all. This suggestion caused enormous distress in the physics community. Wolfgang Pauli, the Austrian theoretical physicist, was having an extraordinarily difficult year in 1930. His mother had committed suicide 2 years earlier. His marriage had already collapsed. He had been seeking help from the psychoanalyst Carl Jung. But through all of this personal turbulence, physics remained his consuming preoccupation. And the beta decay problem would not leave him alone. On December 4th, 1930, Pauli did something unusual. Rather than publish a paper, he wrote a letter. Addressed to his colleagues attending a physics conference in Tübingen, which he was unable to attend himself, Pauli opened the letter with the phrase, "Dear radioactive ladies and gentlemen, He went on to propose what he called, in his own words, a desperate remedy. He suggested that perhaps the missing energy in beta decay was not disappearing at all. Perhaps it was being carried away by an entirely new particle, a particle that no one had ever seen, a particle that was electrically neutral, had spin 1/2, and was somehow light enough to have escaped detection in all previous experiments. Pauli's proposal was breathtaking in its audacity. He was suggesting that nature was hiding a fundamental particle from us, and that it was doing so by making that particle interact so weakly with everything else that it was essentially invisible. He called the hypothetical particle a neutron, though he meant something very different from what we now call by that name. When James Chadwick discovered the actual neutron in 1932, a particle sitting inside atomic nuclei with roughly the same mass as a proton, the name was taken. The great Enrico Fermi then gave Pauli's hypothetical particle its present name, neutrino, the little neutral one. Pauli himself was deeply conflicted about his own idea. He is reported to have said, "I have done a terrible thing. I have postulated a particle that cannot be detected." He also made a wager, a case of champagne, that no one would ever successfully catch a neutrino. It was not so much that he doubted his own hypothesis. It was that he understood the mathematics well enough to know just how weakly this particle would interact with anything. Detecting something that barely noticed the existence of matter seemed, even to its inventor, like it might be impossible. Enrico Fermi took Pauli's ghost particle seriously. In 1933, Fermi developed a complete mathematical theory of beta decay, incorporating the neutrino into a rigorous framework. His theory was elegant and remarkably successful, accurately predicting experimental observations in a way that had not been possible before. The neutrino went from being a desperate speculation to being a necessary component of the most successful theory of beta decay ever formulated. But Fermi's paper was initially rejected by the journal Nature as being too speculative. It was instead published in an Italian journal and then in German. The scientific world was not entirely ready for the invisible particle. For the next 2 decades, the neutrino existed as a mathematical certainty without experimental confirmation. Physicists needed it. Their equations required it. Every measurement of beta decay was consistent with its existence, but no one had seen one. No one had caught one. The particle remained, as the nickname given to the search would later acknowledge, a poltergeist in the machinery of nuclear physics, present everywhere, leaving its mark, but never showing itself directly. What made the problem harder was a calculation published by Hans Bethe and Rudolf Peierls in 1934. Using Fermi's theory, they computed the probability that a neutrino would actually interact with a proton, the most basic possible target. The answer they got was so small that they concluded in print that there was practically no possibility of observing the neutrino. The cross-section for the interaction was roughly 10 to the power of minus 44 square centimeters. To give that number some context, it is smaller than the geometric cross-section of a proton by a factor of about 20 billion. The neutrino was not just elusive, it was, by the calculations of the day's best physicists, essentially undetectable. But physics has a habit of making the impossible merely very, very difficult. Section 3. Catching the uncatchable. The first detection. The story of how the neutrino was finally trapped is one of the most remarkable episodes in the history of experimental science. It begins with an idea so audacious that it can only be described as born from the culture of a generation that had just built atomic bombs. Frederick Raines was a theoretical physicist who had spent years working in the nuclear weapons testing program at Los Alamos. He was a brilliant and restless man, searching in the early 1950s for a fundamental physics experiment he could sink his teeth into. One day, according to the account he gave many years later, he sat down with a blank piece of paper and asked himself, "What is the hardest experiment in the world?" The answer that came back to him was immediate: detecting the neutrino. The chance. Meeting with Clyde Cowan, a physicist and engineer who had also worked on nuclear weapons testing, happened on a stalled airplane during an unplanned stopover in Kansas City. The two men, confined by circumstance, began to talk seriously. They decided in that conversation to try to do the impossible. Both had the resources, the expertise, and something perhaps most important: the can-do attitude forged in the Manhattan Project and its aftermath, a deep-rooted belief that engineering ingenuity could solve problems that seemed mathematically hopeless. Their first idea was almost operatic in its ambition. They would place a neutrino detector 50 meters from ground zero of a nuclear explosion. Nuclear bombs produce enormous bursts of antineutrinos, and the burst would be intense enough that even a few interactions might be captured. They actually obtained permission from the laboratory director at Los Alamos to attempt this experiment. The detector was to be named, with characteristic humor, El Monstro. It would be lowered into a hole in the ground at the moment of detonation. The plan was eventually set aside, primarily because a nuclear reactor could provide a more sustained and controllable flux of antineutrinos. An atomic bomb gives you one burst. A reactor runs continuously. J.M.B. Kellogg, the Los Alamos physics division leader, suggested the reactor approach, and Raines and Cowan embraced it. Their project was given the code name Project Poltergeist, a name that captured perfectly the nature of what they were hunting. Their first attempt at the Hanford nuclear reactor in 1953 was not conclusive. The background noise from other particles created by the reactor was too high, too difficult to separate from genuine neutrino signals. The detector they had constructed was enormous by the standards of the day, but it was not yet sensitive enough. Rather than giving up, Raines and Cowan refined their design, improved their detection techniques, and looked for a better location. They found it at the Savannah River Nuclear Reactor Facility in South Carolina. The P reactor at Savannah River was exceptionally powerful, and it was possible to position the detector only about 11 meters from the reactor core, while being shielded from most background radiation by thick walls. This was still an extraordinary environment, bathing the experiment in antineutrinos at a rate that gave them a real fighting chance. The detection method they used was ingenious. When an electron antineutrino strikes a proton, it can produce a positron and a neutron. The positron, being antimatter, almost immediately annihilates with a nearby electron, producing two gamma-ray photons in opposite directions. The neutron, meanwhile, slows down over a few microseconds and is eventually captured by cadmium chloride dissolved in the detector's water. The cadmium captures the neutron and emits another gamma ray. So the signature of a genuine antineutrino interaction is very specific. First, A pair of simultaneous gamma rays from positron annihilation, followed a few microseconds later by another gamma ray from cadmium neutron capture. This double coincidence signal was designed to be essentially impossible to fake, requiring the exact sequence and timing to register as an event. For more than 5 months, Rains and Cowan collected data. They analyzed their results with painstaking care. They confirmed that the signal rate changed when the reactor was powered down. They verified that the rate matched theoretical predictions for the antineutrino flux from a reactor. They achieved a statistical significance so high that the probability of the signal being a coincidental background fluctuation was less than 1 in a million. On June 14, 1956, they sent a telegram. It was addressed to Wolfgang Pauli, the man who had invented the particle 26 years earlier. It read, "We are happy to inform you that we have definitely detected neutrinos from fission fragments by observing inverse beta decay of protons. Observed cross-section agrees well with expected 6 times 10 to the power of minus 44 square centimeters. Frederick Rhines, Clyde Cowan." Pauli's reply, sent the next day from Zurich, was a masterwork of measured satisfaction. He wrote, "Thanks for message. Everything comes to him who knows how to wait." Pauli died in 1958, just 2 years later. Before he could see the full flowering of the field his desperate remedy had seeded. Clyde Cowan passed away in 1974. Frederick Rhines lived to receive the Nobel Prize in Physics in 1995, awarded for the detection of the neutrino, the discovery that had been more than 4 decades in the making. It remains one of the most celebrated confirmations of a theoretical prediction in the entire history of particle physics. The significance of the detection extended far beyond simply proving that a particle existed. It established that neutrinos were real, physical objects with measurable properties. It verified that the weak nuclear force operated the way Fermi's theory said it did, and it opened a door. Within the decade, physicists were asking the next question: was there only one kind of neutrino, or were there more? Section 4. 3 flavors of ghost. Neutrino types and properties. In the early 1960s, something unexpected happened that complicated the picture considerably. There was already a known particle called the muon, discovered in 1937 in cosmic ray experiments. The muon behaved in many ways like a heavy version of the electron. It had the same charge, the same spin, but it was about 207 times heavier. The physicist Chuo I. Rabai, on first hearing about the muon's discovery, reportedly asked, with a mixture of wonder and mild exasperation, "Who ordered that?" The muon decayed, and when it did, it produced neutrinos. The question that naturally arose was whether the neutrinos produced in muon decay were the same as the neutrinos produced in beta decay, the ones Rains and Cowan had detected. It seemed like a simple question. As it turned out, the answer was no. An experiment at the Brookhaven National Laboratory in 1962, led by Leon Litterman, Melvin Schwartz, and Jack Steinberger, settled the matter decisively. They used a powerful particle accelerator to produce a very intense beam of muon neutrinos, and they directed it at a detector. What they found was that the muon neutrinos, when they did interact with matter, produced muons, not electrons, always muons. If muon neutrinos and electron neutrinos had been the same particle, you would expect them to produce both electrons and muons indiscriminately. The fact that muon neutrinos always made muons, never electrons, proved that these were two distinct types of particle. Lederman, Schwartz, and Steinberger received the Nobel Prize in Physics in 1988 for this discovery. The muon neutrino was the second flavor of neutrino. A third had to wait until the discovery of the tau lepton in 1975 by Martin Pearl at the Stanford Linear Accelerator Center. Just as the electron had its electron neutrino and the muon had its muon neutrino, it was expected that the tau would have its own tau neutrino. Confirming this required building a very specialized experiment. The tau neutrino was extraordinarily difficult to detect because the tau lepton, which it produces upon interaction, is extremely heavy and decays so quickly that identifying its tracks requires a detector with very precise spatial resolution. The donut experiment, short for direct observation of the NU tau, was designed and built at Fermilab specifically to find the tau neutrino. It used a beam of very high energy protons from the Tevatron accelerator to produce a beam expected to contain at least some tau neutrinos. The detector consisted of the alternating layers of iron and photographic emulsion, materials that could record the tiny tracks left by charged particles. After an immense effort of analysis, the donut collaboration announced in July 2000 that they had directly observed 4 tau neutrino interactions in their detector. The third flavor had been found, completing the family of leptons in the standard model. So we now know that there are 3 types or flavors of neutrino. The electron neutrino, denoted by the Greek letter nu subscript e, the muon neutrino, nu subscript mu, and the tau neutrino, nu subscript tau. Each one is defined by which charged lepton it is associated with in weak interactions. Electron neutrinos produce electrons when they interact. Muon neutrinos produce muons. Tau neutrinos produce tau leptons. Each of these 3 flavors also has a corresponding antiparticle, the antineutrino. The distinction between neutrinos and antineutrinos is related to a property called helicity, which describes how the particle's spin is oriented relative to its direction of motion. In the standard model, neutrinos are always left-handed, meaning their spin points in the opposite direction to their momentum. Antineutrinos are always right-handed. This built-in asymmetry between matter and antimatter is one of the deep strangeness of the weak force. A long-standing and still unresolved question is whether neutrinos are what physicists call Dirac particles or Majorana particles. For most particles, the matter particle and the antimatter particle are genuinely different. An electron is different from a positron. A proton is different from an antiproton. But in 1937, the Italian physicist Ettore Majorana showed mathematically that for a neutral, spinless particle, it was possible for the particle and its antiparticle to be identical. Such a particle would be its own antiparticle. Majorana himself then disappeared under mysterious circumstances in 1938, vanishing while on a ship voyage, and was never seen again, leaving behind a puzzle in both physics and biography. If neutrinos are Majorana particles, it would have profound consequences. It would enable a rare type of nuclear decay called neutrinoless double beta decay, in which 2 neutrons in a nucleus decay simultaneously, emitting 2 electrons but no neutrinos at all. Searching for this process is the goal of several major experimental programs, because confirming it would establish the Majorana nature of neutrinos and shed light on why the neutrino mass is so small. Speaking of mass, there is another extraordinary property of neutrinos that took decades to establish and whose full implications are still being worked out. For much of the 20th century, the prevailing assumption was that neutrinos were perfectly massless. The original standard model of particle physics was constructed assuming this. It seemed natural. They were so light that it was essentially impossible to measure their mass directly. And theoretically, giving them mass required a more complicated model. So for simplicity, the assumption was zero. As we will see, that assumption turned out to be wrong. And the discovery that it was wrong won the Nobel Prize in Physics. Section 5. The solar neutrino problem. When the sun went quiet. Our sun is a neutrino factory of almost incomprehensible productivity. Deep in the solar core, where temperatures reach approximately 15 million degrees Celsius and pressures are extraordinary, nuclear fusion reactions convert hydrogen into helium. The proton-proton chain, the primary fusion pathway in the sun, proceeds through a series of reactions that produce electron neutrinos as a natural byproduct. These neutrinos carry away energy and stream outward from the core at nearly the speed of light. Because they interact so weakly with matter, they pass through the sun's entire mass in just a couple of seconds and arrive at Earth about 8 minutes later. The theoretical physicist John Bacall spent decades calculating, with ever-increasing precision, exactly how many solar neutrinos the sun should be producing and what energy spectrum they should have. His calculations, based on the standard solar model, the best available description of how the sun generates energy, predicted a specific flux of neutrinos at Earth. His friend and collaborator, the radiochemist Raymond Davis Jr., spent an equally long time trying to catch them. Davis built his experiment in the Homestake Gold Mine in Lead, South Dakota, beginning in the mid-1960s. He chose a gold mine because the detector needed to be deep underground, shielded from cosmic rays that would otherwise overwhelm any genuine neutrino signal. The mine provided approximately 1,478 meters of rock overburden, enough to screen out most background particles. The detector itself was wonderfully simple in concept and heroically difficult in practice. Davis filled a large tank with 380,000 liters of perchloroethylene, a common dry cleaning fluid rich in chlorine atoms. The physics behind the detection was an idea originally proposed by Bruno Pontecorvo in the 1940s. When an electron neutrino collides with a chlorine-37 nucleus, it can convert it into an argon-37 nucleus, a radioactive atom that Davis could extract and count. The reaction has a threshold, meaning the neutrino must have at least 0.814 million electron volts of energy, which limited the experiment to the more energetic fraction of solar neutrinos. Every few weeks, Davis and his team would bubble helium through the massive tank to sweep out any argon atoms that had formed. They would purify and collect these atoms and count how many decayed over the following weeks. Over a span of roughly 25 years of operation from 1970 onwards, Davis's experiment detected a total of approximately 2,200 argon-37 atoms. Every single one represented a neutrino that had been born in the center of the sun, streamed through 150 million kilometers of space, burrowed through more than a kilometer of rock, and had the rare fortune of encountering a chlorine atom in exactly the right way. But there was a problem, a severe problem. Problem so persistent and troubling that it acquired its own name in the history of physics. The detection rate Davis observed was only about 1/3 of what Bacall's standard solar model predicted. Davis found roughly 2.56 solar neutrino units, while Bacall's calculations predicted about 7.6 solar neutrino units. The discrepancy was enormous, far larger than any reasonable experimental uncertainty. Davis scrutinized every aspect of his detector, looking for systematic errors. Bacall refined his solar model calculations again and again. The results stubbornly refused to agree. This was the solar neutrino problem, and it would persist for more than 3 decades. The scientific community's initial response was largely skeptical of Davis. Surely the experiment must be wrong. Surely some systematic error was inflating the background or deflating the signal. Davis insisted otherwise. He knew his experiment was sound. Bacall, for his part, remained convinced that his solar model was correct. They wrote a joint paper described their situation humorously. Davis had reached his detector and found it working, and then wrote to Bacall, "We are ready now. Turn on the sun." Through the 1970s and 1980s, the mystery deepened. Other experiments were built to check Davis's work. The Kamiokande detector in Japan, a large tank of ultra-pure water surrounded by photomultiplier tubes, detected solar neutrinos through a different method, observing the faint flash of Cherenkov light when a neutrino scattered off an electron in the water. Kamiokande, and later its much larger successor, Super Kamiokande, confirmed the deficit. They too saw only roughly half the expected number of solar neutrinos. Then came the gallium experiments. 2 independent experiments, SAGE in Russia and GALEX in Italy, detected solar neutrinos using tanks of gallium, a chemical that responded to even lower energy neutrinos than chlorine could detect. These experiments were sensitive to the much more numerous lower energy neutrinos from the basic proton-proton fusion reaction. They also found a deficit. By the early 1990s, the pattern was undeniable. Multiple experiments using different detection methods, different chemicals, different backgrounds, all built in different countries by different teams, were all finding fewer solar neutrinos than the theory predicted. Either the sun was not burning the way we thought it was, or something was happening to the neutrinos on their way from the sun to our detectors. A breakthrough came from an unexpected direction. Heliosismology, the study of sound waves reverberating through the sun, allowed scientists to map out the internal structure of the solar interior with remarkable precision. And these measurements confirmed that Bacall's standard solar model was correct. The sun was burning exactly as the model said it should. The temperature and density profiles matched the predictions beautifully. The sun was producing the neutrinos. They were arriving at the right rate overall, but something was happening to them between the core and the detector. The resolution of the solar neutrino problem required a radical rethinking of what neutrinos were capable of, and it came from a direction that some theorists had been pointing toward for decades. Section 6. Neutrino oscillations, shape-shifting through space. The idea that neutrinos might change from one flavor to another as they traveled had been suggested as early as 1957 by Bruno Pontecorvo, the same physicist who had proposed the chlorine detection method years before. Pontecorvo was an Italian-born physicist who had defected to the Soviet Union in 1950 in one of the more dramatic episodes of Cold War science. From his laboratory in Dubna, outside Moscow, he continued thinking deeply about neutrinos, and he understood something subtle and profound about quantum mechanics that, if it applied to neutrinos, would change everything. In quantum mechanics, particles do not always have definite states. A particle can exist in a superposition of multiple states simultaneously, with the definite state only being resolved when a measurement is made. For neutrinos, Pontecorvo recognized that the neutrino flavor, the property that determines how a neutrino interacts in the weak force, did not have to be identical to the neutrino's mass eigenstate, its definite mass. If the flavor states and the mass states were different, and if neutrinos had different masses, then a neutrino created as one flavor would naturally evolve over time and distance into a superposition of different flavors. Given enough time, or equivalently enough distance, it might be detected as a completely different flavor from the one in which it was created. This process, called neutrino oscillation, is a purely quantum mechanical effect. It has no analog in classical physics. A neutrino born as an electron neutrino, emerging from the sun's core, would begin immediately to oscillate. After some distance, it would have a significant probability of being detected as a muon neutrino or a tau neutrino. Ray Davis's chlorine detector was sensitive only to electron neutrinos, not to muon or tau neutrinos. If 2/3 of the solar electron neutrinos were oscillating into other flavors on their way to Earth, that would explain perfectly why Davis was only seeing 1/3 of the predicted number. There was a further wrinkle. In 1978, two Soviet physicists named Mikheyev and Smirnov built on earlier work by Lincoln Wolfenstein to show that neutrino oscillation could be dramatically enhanced when neutrinos traveled through dense matter. The interaction of electron neutrinos with electrons in ordinary matter is slightly different from the interaction of muon or tau neutrinos with those same electrons. This tiny difference creates what is effectively a refraction effect, similar to how light slows down when it passes through glass. Under the right conditions, this matter effect could cause electron neutrinos to undergo a resonant conversion, transforming almost entirely into muon neutrinos inside the sun's dense interior before they ever reached the vacuum of space. This is now called the MSW effect, after Mikheyev, Smirnov, and Wolfenstein. The definitive confirmation of neutrino oscillations came in two stages. The first came from an unexpected direction, from the sky above us rather than from the sun, when cosmic rays, high-energy protons, and other particles streaming in from space strike the upper atmosphere of the Earth. They produce showers of secondary particles. Among these secondary particles are pions, which decay into muons and muon neutrinos, and those muons in turn decay into more muon neutrinos and electron neutrinos. The flux of these atmospheric neutrinos should be predictable, and in particular the ratio of muon neutrinos to electron neutrinos should be well determined. The Super Kamiokande detector in Japan, a colossal tank containing 50,000 tons of ultra-pure water lined with more than 11,000 sensitive light detectors, began taking data in April 1996. By 1998, the Super Kamiokande collaboration had analyzed 535 days of data containing approximately 5,400 atmospheric neutrino events. What they found was astonishing. Atmospheric neutrinos that came from directly overhead, having traveled only about 20 to 30 kilometers from where they were created in the upper atmosphere, showed up in roughly the expected numbers. But atmospheric neutrinos coming from below, having traveled through the entire diameter of the Earth, a journey of up to about 13,000 kilometers, showed a dramatic deficit. There were only half as many upward-going muon neutrinos as there should have been. The pattern was unmistakable. Muon neutrinos were disappearing over long distances, and the pattern matched precisely what would be expected if muon neutrinos were oscillating into tau neutrinos as they traveled. Tau neutrinos interact too weakly with the detector's water to produce the kind of energetic tracks that Super Kamiokande was designed to see, so they were effectively invisible. They had not disappeared. They had transformed. At the 18th International Conference on Neutrino Physics and Astrophysics in Takayama, Japan, in June 1998, the Super Kamiokande collaboration announced their result to an audience of about 400 physicists. The primary statistical significance was more than 5 standard deviations, essentially the gold standard of discovery in particle physics. Neutrino oscillations had been discovered. Takaki Kajira, who led the analysis, later described the moment of seeing the evidence emerge from the data as one of the most exciting of his scientific life. The solar neutrino problem was solved 2 years later by a detector in Canada. The Sudbury Neutrino Observatory, or SNO, was built in an active nickel mine in Ontario at a depth of more than 2 kilometers. Unlike previous water detectors that used ordinary water, SNO used 1,000 tons of heavy water, water in which the hydrogen atoms are replaced by deuterium, a heavy isotope of hydrogen. This gave SNO a unique capability. It could detect not only electron neutrinos, but also through a different reaction, all 3 neutrino flavors equally. For the first time, an experiment could ask the total question: how many neutrinos of any flavor are arriving from the sun, not just electron neutrinos? In June 2001, the SNO collaboration announced their result. When they counted only electron neutrinos, they got the same reduced number that Davis and Kamiokande had seen. But when they counted all neutrino flavors, the total matched the standard solar model's prediction beautifully. The neutrinos were not missing. They had changed flavors. Electron neutrinos, born in the sun's core, were arriving at Earth as a mixture of all 3 flavors. John Bacall, upon hearing the result, was reported to have said simply, "I feel like dancing, I'm so happy." After nearly 40 years of work, the puzzle was solved. Kajita and Arthur MacDonald of the SNO experiment were awarded the 2015 Nobel Prize in Physics for the discovery of neutrino oscillations. The Nobel Committee noted that their work demonstrated that neutrinos have mass, which requires an extension of the standard model of particle physics. What neutrino oscillations mean for the deeper structure of physics cannot be overstated. The fact that neutrinos oscillate tells us, mathematically and inescapably, that they have mass, not zero mass, some small but non-zero mass. The standard model, as originally written, assumed massless neutrinos. That assumption is now known to be incorrect. Neutrinos have mass, and mass changes everything. Section 7. Cosmic neutrinos. Messengers from supernovae and beyond. One of the most extraordinary moments in the history of astronomy occurred in the early morning hours of February 23, 1987. A blue supergiant star inside the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, about 168,000 light-years away, collapsed catastrophically at its core. The core, compressed beyond the point of nuclear stability by its own gravity, imploded in a fraction of a second, forming a neutron star and releasing an amount of gravitational energy equivalent to roughly 3 times 10 to the power of 53 ergs, more energy than our sun will emit over its entire 10 billion year lifetime. But this energy was not released as light, at least not primarily, in the seconds immediately following the collapse, when the density of the forming neutron star was so extreme that even neutrinos could barely escape. The energy was released as an enormous burst of neutrinos and antineutrinos. About 99% of all the energy released in a core collapse supernova comes out as neutrinos. The light, the spectacular explosion we see across the sky, is powered by just 1% of the total energy budget, the neutrino burst. From this supernova, which came to be known as SN 1987A, traveled 168,000 light-years and arrived at Earth about 3 hours before the visible light of the explosion. This is because neutrinos, interacting only weakly with matter, could stream out of the collapsing core immediately. The optical light had to wait for the shock wave to travel outward through the star's outer layers before it could escape. At 7:35 Universal Time on February 23, 1987, 3 underground neutrino detectors registered the signal within seconds of each other. The Kamiokande 2 detector in Japan detected 11 events in 13 seconds. The Irvine, Michigan Brookhaven detector in the United States detected 8 events. The Baksan scintillation telescope in the Soviet Union detected 5 events. In total, 24 neutrinos were directly observed from SN 1987A. To appreciate the significance of this, consider that 168,000 years of travel through space, followed by passage through the entire bulk of the Earth, still left these particles energetic enough to produce detectable events in ton-scale detectors built in mines. The universe had just sent us a message, and we were just barely equipped to receive it. These 24 neutrinos told physicists an enormous amount. They confirmed that the core collapse model of supernovae was fundamentally correct. The energy budget, the duration of the burst, the energies of the individual neutrinos, all matched theoretical predictions with remarkable precision. The observations also placed a limit on the neutrino mass. If neutrinos had significant mass, the more energetic ones would have traveled slightly faster than the less energetic ones, arriving at slightly different times. The fact that neutrinos of different energies arrived within seconds of each other placed an upper limit on the neutrino mass of less than about 20 electron volts. The neutrino had to be extraordinarily light. Masatoshi Koshiba, the leader of the Kamiokande experiment, shared the Nobel Prize in Physics in 2002 with Ray Davis for the detection of cosmic neutrinos, an award that recognized this extraordinary moment in neutrino astronomy, as well as Davis's 3 decades of solar neutrino work. The detection of SN 1987. A neutrinos marked the birth of neutrino astronomy. For the first time, humans had used particles other than light to observe a specific astronomical event at a known location in space. This was the opening of a new window on the universe, one that complemented optical astronomy, radio astronomy, X-ray astronomy, and all the other ways we had previously studied the cosmos. But SN 1987A, for all its significance, was still close by, cosmologically speaking, and the energies of its neutrinos were modest, in the range of a few to tens of millions of electron volts. As physicists built larger and more sophisticated detectors, they began to wonder about neutrinos from far more violent sources, from the energetic hearts of distant galaxies, from gamma-ray bursts, from the most extreme environments in the observable universe. These sources should produce neutrinos at energies millions or billions of times higher than those from SN 1987A. The instrument that opened this next chapter was IceCube. IceCube is perhaps the strangest scientific instrument ever built. It is a neutrino detector sitting at the South Pole, but it doesn't look like anything you might imagine a detector to look like. It consists of 5,160 basketball-sized glass spheres, called digital optical modules, suspended on 86 cables, drilled down into the ice of Antarctica. The cables descend to depths of up to 2.5 kilometers below the surface of the ice sheet, and the optical modules are spaced along each cable, creating a three-dimensional array of light detectors embedded in a cubic kilometer of some of the clearest, most transparent natural material on Earth. The Antarctic ice, deep below the surface, is under immense pressure. It has been there for hundreds of thousands of years, and over that time, air bubbles have been forced out, leaving behind ice of remarkable optical clarity. When a high-energy neutrino passes through this ice and happens to interact with a water molecule, it creates a flash of blue light called Cherenkov radiation, a form of electromagnetic shockwave produced when a charged particle travels through a medium faster than light travels through that same medium. The light spreads outward and is detected by the nearby optical modules. By analyzing the pattern, timing, and brightness of the light signals across multiple modules, IceCube can reconstruct the energy and direction of the original neutrino. In November 2013, the IceCube collaboration announced a result that sent a wave of excitement through the scientific community. They had detected 28 very high-energy neutrino events that could not be explained by the expected background of atmospheric neutrinos. These events had energies ranging from tens of tera-electron volts up to about 2,000 tera-electron volts, with two events near a peta-electron volt, which is 1,000 tera-electron volts. For context, the most energetic neutrinos detected from SN 1987A had energies around 30 to 40 million electron volts. These IceCube neutrinos were tens of millions of times more energetic. They could only have come from outside the solar system, from astrophysical sources of extraordinary power. IceCube had detected for the first time neutrinos from the deep cosmos, from the great cosmic accelerators that physicists had been hunting for decades. In July 2018, a single exceptionally high-energy neutrino arrived at IceCube with an estimated energy of 290 tera-electron volts. IceCube's automated alert system triggered, and telescopes around the world were directed to look at the region of sky from which it had come. A blazar, an active galaxy with a supermassive black hole powering two enormous relativistic jets aimed roughly toward us, was found to be flaring with gamma rays at the same time in the same direction. The blazar, designated TXS plus 056 sits about 4 billion light-years from Earth. For the first time, a specific cosmic object had been identified as a high-energy neutrino source. The era of multi-messenger neutrino astronomy had arrived. More recently, in November 2022, the IceCube collaboration announced an even more compelling result. Over 11 years of data collection, they had accumulated strong evidence for 79 high-energy neutrinos coming from the galaxy Messier 77, also known as NGC 1068. This galaxy, 47 million light-years away, harbors an active galactic nucleus, a supermassive black hole with a thick surrounding torus of dust and gas. The neutrinos appear to originate in the densely energetic environment near the black hole, passing through the obscuring dust that hides the innermost region from optical and gamma-ray telescopes. The neutrinos, ghost-like as always, traveled through it all and reached our ice. Section 8. The Mass Mystery. Weighing something that barely exists. We have established that neutrinos have mass, but the question of how much mass they have and what the exact masses of the three types are remains one of the most pressing and unresolved questions in fundamental physics today. The fact that neutrinos have mass was not anticipated by the original Standard Model. For decades, the assumption of massless neutrinos was built into the theory's foundations. When neutrino oscillations proved that mass was real, the Standard Model had to be modified. But modified in what way? Adding neutrino mass to the theory is not straightforward. There are several mathematically consistent ways to do it, and they make different predictions about the nature of the neutrino. One critical point: neutrino oscillation experiments, no matter how precise, can only measure the differences between the squares of the neutrino masses. They tell us that the mass of the second type minus the mass of the first type squared is a certain value. They tell us the same for the second and third types, but they cannot tell us the absolute scale. Even if we know all the mass differences, we still do not know whether the smallest neutrino mass is 0, or a millionth of an electron volt, or 100th of an electron volt. The ordering of the masses is itself unknown. There are two possibilities physicists call the normal hierarchy, where the first mass state is lightest and the third is heaviest, and the inverted hierarchy, where the third is lightest and the first and second are heaviest. Determining which ordering is correct is a major goal of current and future experiments. Measuring the absolute mass is technically daunting, but it is the goal of one of the most ambitious experiments in contemporary physics, the Katrine experiment in Karlsruhe, Germany. The Karlsruhe tritium neutrino experiment uses the beta decay of tritium, an unstable isotope of hydrogen, to probe the neutrino mass. When tritium decays, it emits an electron and an electron antineutrino. These two particles share the available energy between them. If the antineutrino has mass, it must always carry away at least the energy equivalent of its rest mass. This means the electron spectrum must have a very slight deficit at the highest energies, where the antineutrino would have minimal kinetic energy, but still needs to carry its mass energy. Katrine's spectrometer is among the largest and most precise scientific instruments ever built. It is a 200-ton device, 10 meters in diameter and 23 meters long, maintained at an ultra-high vacuum, designed to measure the energies of individual electrons with a precision of a fraction of an electron volt. The tritium source it uses is the most intense ever created for this purpose. In 2022, the Katrin collaboration published an upper limit of 0.8 electron volts per speed of light, squared for the neutrino mass. This was the first time any direct neutrino mass experiment had entered the sub-electron volt range. By 2025, after 5 measurement campaigns totaling roughly 259 days of data collection, the upper limit had been tightened to 0.45 electron volts, nearly halving the previous constraint and setting a new world record. To appreciate how remarkable this number is, consider that the electron, the lightest charged particle, has a mass of about 511,000 electron volts. The lightest neutrino has a mass less than 0.45 electron volts, meaning it is at least 1,000,000 times lighter than the electron, which was itself long considered one of the lightest particles in existence. The neutrino mass is almost vanishingly small, and yet it is not zero. This tiny mass has macroscopic consequences. Because neutrinos are so abundant, with about 340 of them in every cubic centimeter of space throughout the universe, their collective mass influences the large-scale structure of the cosmos. Massive neutrinos stream through the universe freely, but their gravity, however slight, affects how matter clusters and how galaxies form. Heavier neutrinos would have smoothed out structure on small scales, suppressing the formation of dwarf galaxies and small clusters. Cosmological observations, which can constrain the neutrino mass through their effect on the distribution of galaxies and on the cosmic microwave background, suggest that the sum of all 3 neutrino masses must be less than about 0.12 to 0.2 electron volts, depending on the cosmological assumptions made. The Katrin experiment is expected to reach a final sensitivity of about 0.3 electron volts by the end of its measurement campaign. Beyond Katrin, the next generation experiment called Project 8 aims to use a completely new technique, measuring the frequency of radio waves emitted by individual electrons in a magnetic field, to push the sensitivity to about 0.04 electron volts. These experiments are hunting for one of the most elusive measurements in all of physics, weighing, something that is both everywhere and almost massless. The smallness of the neutrino mass itself is a profound theoretical puzzle. Why are neutrinos so light? One compelling theoretical framework, called the seesaw mechanism, offers an elegant answer. It proposes that there exist very heavy counterparts to ordinary neutrinos, called right-handed neutrinos or sterile neutrinos, with masses perhaps at the grand unification scale, somewhere around 1 trillion times the mass of a proton. The mathematical structure of the theory would then naturally produce the ordinary light neutrinos we observe, with masses that are inversely proportional to the masses of the heavy counterparts. The heavier the right-handed neutrino, the lighter the left-handed one would be. This seesaw relationship could explain why the neutrino masses are so extraordinarily small compared to all other known particles. If this framework is correct, it has a further remarkable implication. In the hot early universe, these enormously massive right-handed neutrinos would have been produced and would have decayed. If their decays violated the symmetry between matter and antimatter, those decays could have generated a slight excess of leptons over antileptons, the basic building blocks of atoms. Electroweak processes in the early universe could then have converted this lepton asymmetry into the baryon asymmetry that made our matter-dominated universe possible. This is called leptogenesis, and it connects the tiny mass of the neutrino to the very existence of everything we can see. Section 9. The Great Detectors. Temples built to see the invisible. One of the most quietly extraordinary things about the science of neutrinos is the infrastructure that has been built to study them. The major neutrino detectors of the world are remarkable not just as physics experiments, but as human achievements, as demonstrations of what sustained ingenuity and collective effort can construct in service of understanding. The Homestake experiment, Ray Davis's first great contribution to neutrino physics, was in some ways the simplest of the breed. A tank the size of a modest swimming pool, more than a kilometer underground, filled with dry cleaning fluid, and maintained with meticulous care for more than 25 years by a small team of devoted scientists. Davis once reported having detected the argon atoms produced by solar neutrinos at a rate of less than 1 atom per day on average, from a tank containing 100,000 gallons of liquid. The patience and precision required for this work is almost impossible to overstate. Super Kamiokande, which succeeded the earlier Kamiokande experiment, sits 1,000 meters below the surface in the Mozumi mine in Hida, Japan. The detector contains 50,000 tons of ultra-pure water in a cylindrical tank 41 meters across and 41 meters tall. The inner surface of this cylinder is lined with 11,129 photomultiplier tubes, each 50 centimeters in diameter, sensitive enough to detect individual photons of light. The water in the tank must be kept extraordinarily pure because any impurities scatter the delicate Cherenkov light flashes and reduce the detector's sensitivity. Maintaining this purity requires continuous filtration and monitoring. The water is so pure, in fact, that if you were to stand inside the tank, you would be in danger. Water that pure actively dissolves minerals from human skin. The water itself is physically hazardous to touch in the way that water can become when stripped of essentially all impurities, a molecular solvent hungry for anything it can take. The researchers who work inside the detector during maintenance periods wear protective suits and work quickly and carefully. In November 2001, Super Kamiokande suffered a catastrophic accident. During the installation of new photomultiplier tubes, one tube imploded under the pressure of the water. The implosion generated a shock wave that propagated through the tank and triggered a cascade of further implosions, destroying about 6,600 of the 11,129 photomultiplier tubes in a chain reaction. The accident was a devastating blow to the collaboration. Months of careful work were required just to assess the damage, and years of reconstruction followed. The detector was eventually restored and upgraded with protective enclosures around each tube to prevent any future cascade events. Super Kamiokande continues operating today, still producing fundamental measurements. Its successor, Hyper Kamiokande, is currently under construction with a fiducial volume roughly 8 times larger, scheduled to begin taking data in 2027. The Sudbury Neutrino Observatory, which solved the solar neutrino problem, occupied a different underground environment. The SNO detector was built in a nickel mine in Sudbury, Ontario, Canada, at a depth of about 2 kilometers. The heart of the detector was a 12-meter acrylic sphere filled with 1,000 tons of heavy water, surrounded by a larger sphere, and then by ordinary water that served as shielding. The acrylic sphere was supported by a web of ropes and cables that had to be designed to absolute cleanliness standards, because any radioactive contamination in the water or on the vessel surfaces would produce background events indistinguishable from genuine neutrino interactions. The SNO collaboration invested enormous effort in materials characterization and contamination control, techniques that have since become standard across the field. The SNO experiment has since been transformed into SNO Plus, with the heavy water replaced by a liquid scintillator, and the scientific focus shifted to searching for neutrino-less double beta decay, the process that would confirm the Majorana nature of neutrinos. Then there is IceCube, which we have already encountered, a detector unlike any other. The construction of IceCube required drilling 86 holes in the Antarctic ice sheet, each hole about 2.5 kilometers deep and 60 centimeters wide. The drilling used a custom hot water drill that melted its way downward through the ancient ice, taking about 40 hours to reach full depth. Once a hole was completed, a string of 60 digital optical modules was lowered in, and the water froze back around them, locking the instruments into their precisely engineered positions in the ice. The entire construction process took 7 years, with teams working at the South Pole through the austral summer season, one of the most demanding construction environments on Earth. The final string was deployed in December 2010. Below the surface, the light from neutrino interactions takes microseconds to reach the optical modules. Above the surface, the signals travel by fiber optic cable to computing facilities at the Amundsen Scott South Pole Station, where they are processed in real time, and, for the most interesting events, alerts are automatically sent within minutes to astronomers around the world. IceCube has become a node in a global network of observatories, a way station in the emerging infrastructure of multi-messenger astronomy. The Katrin experiment in Karlsruhe is a different kind of monument, where IceCube and Super Kamiokande are large. Because of the need to intercept rare neutrino interactions, Katrin is large because of precision. Its main spectrometer, a hollow ellipsoidal vessel 10 meters in diameter and 23 meters long, weighs 200 tons. It is maintained at a vacuum so perfect that the pressure inside is less than 1/10 of atmospheric pressure, one of the best vacuums maintained continuously in any scientific instrument on Earth. The tritium source, the 70-meter beamline that transports electrons to the spectrometer, and the detector at the far end are all the product of decades of development, involving scientists from more than 20 institutions across 7 countries. And looking to the near future, the landscape of neutrino physics is expanding still further. The Deep Underground Neutrino Experiment, or DUNE, is under construction in the United States. Its near detector will be located at Fermilab outside Chicago, and its far detector will be built deep underground at the Sanford Underground Research Facility in Lead, South Dakota, about 1,300 kilometers away. DUNE's far detector will use liquid argon as its detection medium, a technology that offers far more detailed tracking of particle interactions than water Cherenkov detectors. A beam of neutrinos will be fired from Fermilab through the Earth to the far detector, and physicists hope to use this long baseline experiment to definitively measure the CP violating phase in neutrino oscillations and to determine the neutrino mass ordering. KM3NET, positioned at the bottom of the Mediterranean Sea, follows IceCube's approach of using a large natural body of clear water as the detection medium, but with different technical solutions suited to the sea environment. And Juno, the Jiangmen Underground Neutrino Observatory, is being built in China to study reactor antineutrinos with extraordinary precision and to determine the neutrino mass ordering through very precise measurements of oscillation patterns. Each of these experiments represents an investment not just of money, but of human lives and careers. Physicists spend their entire working lives dedicated to a single detector, a single question, the slow accumulation of data, the patient elimination of background, the statistical analysis of rare events. This is the texture of neutrino physics, methodical and dedicated, sometimes spanning decades from the moment of conception to the moment of discovery. Section 10. What neutrinos reveal about the deepest secrets of the universe. We have traveled a long way tonight, from the crisis in nuclear physics that produced Pauli's desperate remedy, through the decades-long hunt that finally caught the first neutrino, through the discovery of new flavors, and the solar neutrino mystery, and the discovery of oscillations, through the birth of neutrino astronomy, and the ongoing hunt for the neutrino's mass. Now let us step back and look at the full picture, at what the study of these ghost particles tells us about the deepest questions the universe poses. The most profound implication of neutrino physics may be the one that is least resolved. The matter-antimatter asymmetry problem sits at the very center of cosmological mystery. When the universe was born in the Big Bang, the laws of physics as we understand them would have produced equal amounts of matter and antimatter. For every proton, an antiproton. For every electron, a positron. For every quark, an antiquark. These particles and antiparticles would have annihilated each other in the early hot universe, leaving behind nothing but photons. If the universe had been perfectly symmetric, there would be no matter, no galaxies, no stars, no planets, no life, just a universe of light. And yet here we are. The universe is made of matter. Everything we can see, everything we can touch, everything that has ever existed in the form of structured atoms and molecules, and cells and thoughts and civilizations is made of matter, not antimatter. Something in the early universe tipped the balance. For every billion particles of antimatter that were produced and annihilated, there were 1,000,000,001 particles of matter. That tiny 1 in a billion excess is everything. That one particle in a billion that survived the mutual annihilation of the rest is the substance of the universe. What caused this asymmetry? No one knows for certain, but neutrinos offer one of the most compelling and actively studied hypotheses. The measurement of CP violation in neutrino oscillations, the study of whether neutrinos and antineutrinos oscillate at different rates, is one of the central targets of the next generation of experiments. The T2K experiment in Japan, which fires a beam of neutrinos from J-Park on the east coast to Super Kamiokande, 295 kilometers away, has already seen tantalizing hints of CP violation in the neutrino sector. In 2020, T2K published results in Nature showing that the data disfavored perfect CP symmetry at greater than 3 standard deviations, a 99.7% confidence level, though not yet the 5 sigma standard that physicists require to claim a discovery. Electron neutrinos appear to be produced more readily from the oscillation of muon neutrinos than electron antineutrinos appeared to be produced from muon antineutrinos. The behavior was asymmetric. If CP violation exists in the light neutrino sector, it strongly suggests, through the theoretical framework of leptogenesis, that the analogous asymmetry would exist in the heavy right-handed neutrinos that many physicists believe must exist. In the hot early universe, those heavy neutrinos, produced abundantly in the extreme temperatures of the first fractions of a second, would have decayed in a slightly asymmetric way, producing slightly more leptons than antileptons. The subsequent physics of the electroweak era would have converted that lepton asymmetry into the baryon asymmetry that made the matter-dominated universe possible. This connection, from the oscillations of a ghost particle that slips through your body right now to the fundamental question of why the universe contains anything at all, is one of the most beautiful threads in all of science. It suggests that in studying neutrinos, we are studying the mechanism that made our own existence possible. There are other profound questions where neutrinos hold clues. Dark matter, the mysterious invisible substance that accounts for roughly 27% of the universe's total energy density, has not yet been identified. Neutrinos were once serious candidates for dark matter, but cosmological observations have shown that their masses are too small for them to account for the observed dark matter. Nevertheless, hypothetical, heavier types of neutrinos, particularly sterile neutrinos with masses in the kilo-electron-volt range, remain active candidates. Katrin's next phase, the Tristan upgrade, will search specifically for these sterile neutrinos. Finding them would solve two problems at once, providing both an explanation for the seesaw mechanism of neutrino mass generation and a candidate for the dark matter. Neutrinos are also key probes of extreme astrophysical environments. The dense cores of collapsing stars, the jets of material launched from merging neutron stars, the turbulent environments of active galactic nuclei around supermassive black holes. All of these produce neutrinos that escape even when light cannot. In the era of multi-messenger astronomy, where gravitational wave detectors and gamma-ray telescopes and optical observatories all work in concert to study the same cataclysmic events, neutrinos are one of the most powerful messengers available. The next nearby supernova in our galaxy, or in a satellite galaxy, would produce a burst of neutrinos detectable by multiple instruments simultaneously, providing an unprecedented window into the moment of stellar collapse and the formation of neutron stars or black holes. And then there is the cosmic neutrino background, the oldest relic we can ever hope to detect. When the universe was about 1 second old, the temperature had fallen to the point where neutrinos stopped interacting frequently with other matter. They decoupled, streaming freely through space from that moment on. Since then, they have been everywhere, cooling as the universe expanded, losing kinetic energy but never disappearing. Today, the cosmic neutrino background fills the universe with about 340 neutrinos per cubic centimeter of space, a number that includes all 6 types, neutrinos and antineutrinos of all 3 flavors. Their temperature today is about 1.95 Kelvin, colder than the cosmic microwave background's 2.725 Kelvin because they decoupled slightly earlier and didn't receive the extra energy from electron-positron annihilation that the photons did. We have never directly detected the cosmic neutrino background. Its neutrinos are so cold, so low in energy, that they are even further below our current detection capabilities than any other class of neutrinos we have studied. An experiment called Ptolemy, proposed for the Gran Sasso underground laboratory in Italy, hopes to make a first measurement of these ancient particles using tritium as a target, exploiting the fact that a relic neutrino captured by a tritium nucleus would produce an electron with a slightly different energy signature than a neutrino from any other source. If successful, it would give us the first direct view of particles that have been free streaming through the universe since its first second, older than any star, older than any atom, witnesses to every era of cosmic history. There is something almost meditative about the neutrino, something that rewards slow contemplation. It has been with us since the beginning. It was created in the first violent moments after the Big Bang, and it has been flowing through the universe ever since, untouched and unbothered by the drama of galaxy formation, star formation, the birth and death of suns, the condensation of planets and oceans and atmospheres, the long, slow development of life and consciousness and civilization. None of it, not any of it, slowed the neutrino down or changed its direction or left the faintest mark on its trajectory. And yet studying it has given us new tools to probe the universe's most important questions. Through the neutrino, we have confirmed how the sun burns. We have watched a star die 168,000 light years away. We have traced particles back to supermassive black holes, billions of light years distant. We have discovered that particles can change their nature as they travel, that mass and flavor are not locked together but woven in a quantum dance across distance. We have found hints that the symmetry between matter and antimatter may be broken in a way that could explain why we exist. All of this from something you cannot see, cannot feel, that passes through your body in its billions every second, leaving no trace, asking nothing of you. The universe is deep, and it speaks in many languages. Neutrinos are one of the oldest and most faithful messengers in the cosmos, carrying information from the innermost furnaces of stars, from the most violent explosions in existence, from the very first second of time. We have spent less than a century learning to listen to them. We are still, by any honest reckoning, in the earliest chapters of that education. What will the next discoveries bring? Hyper Kamiokande, when it opens in 2027, will catch neutrinos with 8 times the sensitivity of its predecessor, and may confirm CP violation in neutrino oscillations within a decade. Dune, when its beam comes online, will make precise measurements of the mass, ordering, and the CP violating phase, and will be ready to observe the next galactic supernova with unprecedented detail. Katrin will approach its final sensitivity, possibly the first direct measurement of actual neutrino mass. Project 8 and its successors will push even further. IceCube Gen 2, an expanded version of the South Pole Observatory, will hunt for the sources of the highest energy cosmic neutrinos in deeper detail. The neutrino has led us to 4 Nobel Prizes in physics and counting. It has rewritten our understanding of particle physics, of stellar astrophysics, of the large-scale structure of the universe. And it has done all of this while barely interacting with anything. There is something deeply poetic about that. The most abundant matter particle in the universe, the one that travels through everything and interacts with nothing, turns out to hold the answers to some of our most fundamental questions about the nature of existence. The next time you look up at the sun on a clear day, or stand outside on a dark night and feel the peaceful expanse of the sky above you, know that you are surrounded in every direction at every moment by the most prolific particles in the universe. They have come from stellar cores and collapsing stars and the violent hearts of active galaxies, and they stream through you as though the universe were telling you something, quietly and continuously, in a language we are only just beginning to understand. We are made of the same ancient atoms as the stars, and we are bathed always and everywhere in the oldest light the universe cannot even hold, the neutrino tide, streaming from the depths of space through the earth, through us, and on into the infinite dark beyond. Thank you for joining me tonight on this long, quiet journey through the world of the ghost particle. If this exploration brought you peace or wonder or just a pleasant place to rest your mind, please leave a like and consider subscribing to Sleepy Universe. Each one helps more curious minds find their way here. Until next time, rest well and know that the universe continues its gentle ancient work all around you, even in the dark. Good night.